using liberate tool. We have generated few of the files. So one of the important file that we have generated is the standard lib.lib, okay, so which is the library file that we have generated. And apart from these, what are the other files that we have generated? Yeah, lef was basically using abstract, right? So that is generated out of the abstract tool, but we have made use of this liberate tool to generate a .lib file. But apart from this .lib file, we have also generated few other files. So yeah. So we have generated two sets of Verilog files, right? So yeah, std lib dot I think nd.v, and the other one is std lib d.v. Okay, so these are the two Verilog files that we have generated, and finally we also generated some HTML files. Okay, so now this is what we had it in our liberate, or I don't know what extension we had given for the directory. So I think lib or something we have given, I guess, right? So the directory name that we have used to generate these things, we have I guess it is lib is the library name that we have given, I guess. Sorry, the directory name that we had given. So in that file, we just invoked this liberate tool and we generated all these 4 files. Okay. Now, apart from this, we also have to create few other directories. So under your RV 19EC and whatever the number, right? So under this directory, we had this lib directory, and we also had layouts. Okay. Now apart from this, we will be creating few more directories, which is RTL. There is one of the directory that we are going to create, and then synthesis is one more directory, and then this is not really necessary for today's experiment. Okay, the physical design directory. Okay, so we are not going to touch upon this, but later on in the next experiment we will be touching upon this physical design. But as of now, from under this directory, we generally have this 5 different directories. Okay, now, so as I said, under this lib directory, we have all those 4 files that have been generated. Now, what we do is that I'm just going to create this RTL directory, and inside this RTL directory, we are going to build a full-adder .v file, and we will also create one more Verilog file, which is the test bench for this full-adder design. Okay, so now in order to check the functionality of this particular full-adder, we are going to use a tool named as nclaunch. Okay, so nclaunch will help us to check the functionality of the design that you have written in the Verilog code. Okay, so we'll be making use of both these files to perform this functional verification using this nclaunch. Now, once this nclaunch or once the functional verification is done, then what we do is that we will go for synthesis process. Now, inside the synthesis process, we need to have one more important file, which is an SDC file. So I have given a name, something like add.sdc. Okay, so I would encourage you to go back and watch that YouTube wherein I have spoken about what is contained inside this SDC file. Okay, so you have to be aware of what exactly is inside this SDC file. Clear? Yeah. So now, first, let us begin with this particular process, and under synthesis folder, what we do is that we will be invoking one more tool, which is RTL compiler RC, okay, with a command GUI. Okay, so these are the 2 tools we are going to explore today, and first we will do the function verification of this .v file, and we go for synthesis, and the output of the synthesis would then again be used by this nclaunch to check the generated netlist is performing the same functionality or not. Okay, so it is something like begin with this nclaunch, go to this RC, and then come back to this nclaunch, okay, with the generated netlist. So now let me do the same thing. I'll just try to log in. So I have already created those files under this RTL directory. Okay, so the Verilog files. Okay, so I'll just open and show what is there inside this. I'll be using some gedit editor. Yeah. So since it's an RTL code, we'll be using a clock signal. Okay. So whenever the clock has a positive edge, then I'm just checking for a reset signal. If the reset signal is enabled, then whatever the input might be, I'll be enabling, or I'll be outputting an output of 0 and 0 for sum and cout. Else what we do is that we'll try to compute the inputs of A, B and C in, and then put the outputs of sum and cout. Clear? So this is it's a very simple Verilog code, and the test bench, I'll show even the test bench that I have. Okay. So the test bench is again is a module that has been defined without any kind of list with it. Okay. So I guess everyone is familiar with the Verilog, right? Yeah. And then I'm just calling the same module that I have defined here. Okay. So whatever the module name that I have defined, I'm just calling it, and I'm applying all the type of inputs and outputs that is required by this particular instance. And then I'm trying to apply my inputs for clock. I first initialize the clock value with 0, and then I'm just running this clock for every 5. So what is this this particular symbol #5 denotes? What is the time period of that? Huh? Yeah, after 5 units. Okay, so how to define a time unit of in Verilog? Yeah, using the time scale. Okay, so there is a time scale that I've defined here. So in this time scale, every unit is defined as 1 nanosecond, and it's a precision, which means that the subdivision inside between 1 nanosecond to 2 nanosecond, the subdivisions levels are being measured in terms of 10 picoseconds. Okay, so that is what is defined here, and I apply all those signals. I think I don't need to talk about much about this. You'll be much more familiar than me. So this is the code that I have. Now let us try to invoke our tool, which is nclaunch. So again, NC stands for native compiler. Okay. So which is a tool from the Cadence. So note that I'm just invoking from this RTL directory. Okay. So where I have kept my codes of full adders. Okay. Now, as you could be able to see that the directory that is right now pointing is not exactly the directory where I have kept my .v files. Okay, it is pointing to some different directory. Okay, so it is better. What you can do is that you just click on this file and click on the set design directory, and ensure that the directory that you wanted to create is being mapped properly. So I just go to the parent directory and then get into the RTL, and in this I'll select this RTL as my design directory and click OK. Now there is also one more option that we have to enable, is the library mapping. Okay. Now just click on this create cds.lib file in the directory where you have kept all your design files. Okay, so I'm just clicking on this create cds.lib file, and I'm locating in the same location where I had my designs. Okay, so click on save, and this will ask for some options. You just go with the default options. Okay, do not change any of the settings here. Just click OK, and then click OK here. Okay. Now whatever I've done till now, the set design directory. Okay, so this option is done only once. Clear? Only for the first time you need to do it, and then just click OK, and everything is cleaned up, and whatever is there in this RTL directory is being listed here. Okay. Now there is a work lib. Right now under this work lib nothing is available. Okay, and even under the snapshots nothing is available. Okay, so now basically using this nclaunch we are going to perform some three major operations. Okay, first I will list out what are those operations, and later I will just come back to this tool and I'll talk about it. Okay. So using nclaunch we are going to perform three operations. The first operation is nothing but the compilation. The second one is the elaboration, and the third one is the simulation. Okay. Yeah. So during this compilation, what we exactly do is the syntax check. Okay, so we'll just be verifying whether the syntax that we have written is proper or not. Okay, so that is the main task of this compilation process. Okay, and as the name implies, once you are clear with this syntax check, then it also generates few things. Okay, so I'll discuss in the tool itself. Okay, so the output of this would be under this work lib. Okay, so the compilation will result in something that results in a kind of file under this work lib. Okay, so I'll talk about this using the tool. The next thing is the elaboration. Okay, so now during the elaboration, what it does is that it performs two things. One is it checks for the connectivity and the existence of instances. Now, before I explain, let me just check with you people, like what could be these, what could be the elaboration means in general, if you would have already come across it. Okay, I think no need to be too much of silence, you can just talk actually. Okay, yeah, say for example, I just want to build a full adder. Okay, so this full adder could be built by making use of half adders as well, right? So I have to have like something like an half adder. Okay, so let me take two half adders, and I think one of the half adders I will just put it in front, and A, B are the two inputs to the first half adder, and C in to be the second input to the second half adder, and the output of the sum is being fed as one of the input to the second half adder, and again it produces two kind of outputs. Okay, one is the sum, the other one is the carry. I'll use the carry here, and there is also a carry. So what we do is that we generally OR these two carries and output this as our carry out, and this output is directly taken as a sum, right? Yeah. So now what exactly is that? When I try to write this kind of code in a structural way, what happens is that I will be using something like, say for example, the module name of the half adder is HA. Okay, and then I just give some sort of instance name for it, and then I just apply its inputs of A, B, as well as your sum and carry out. So all of these things have been done, and during the compilation, what happens is that it checks only the syntax, but it never checks whether that half adder is already exist or not, right? So during the second elaboration process, it goes and checks whether the half adder is already exist in your work library or not. If not, it throws an error. Okay, so that is what we actually do in the case of an elaboration. It goes deep down the hierarchy level, check whether every components are available in your work library, and if it is so, it gets connected. If it is not there, then it throws an error. Okay, and that is what we mean by this elaboration. And obviously the third step is pretty much the same, like simulation. So here we will be performing some sort of functional verification, where we will try to apply some set of inputs as a test vectors and try to verify the outputs and check whether your intended operation has been outputted or not. Okay, and that's the only thing. And in general, it's a kind of timing analysis. Okay. Yeah. So with this intro, what we do is that we'll just try to get into the tool. Okay. So first, what I do is that when I try to, according to the first step, we have to perform this compilation. Okay. So select this particular file and go for vlog. Some extension is there, right? Some icon. Okay. So click on this vlog, and the moment I do that, there is no error that happens here. If there is any error, you will have some sort of red color highlight in this comment section. Okay, or in this, what do we call this? Some entry command entry section. Okay, and also right now you could able to see this work lib is being populated with something, and you could able to see that there is a plus sign. Okay, so now when I expand this plus signature, you would be able to see that the module name that I have used inside this full adder is being reflected here. Okay, yeah. So now let me try to compile the test bench as well. So select this and click on this vlog, and again the moment I compile this, you see the module name of my test bench is also being reflected here. Okay. Now among these two files, which one is the topmost module? Test bench is the topmost module, because inside the test bench I'm just calling this full adder. Okay, so the topmost module here is the test bench. Okay, so now what I do is that I'll just select this test underscore FA or the full adder, okay, which is the topmost module right now, and I'm just going to do an elaboration. So inside this test bench, what I've done is that I've called my full adder with an instance name, and now what it does is that it goes during the elaboration, it goes and checks whether this particular full adder is there in any of these libraries, or at least it will just check whether I have it in my work lib or not. Okay, if it is not so, it throws an error. So now what I do is that let me try to delete this. Okay, I don't have this full adder. I'll delete this and let me try to elaborate right now. Now this full adder I have called here will not be available in any of these libraries nor inside this work lib, right? So it has to throw an error. We'll just see what happens right now. So select this topmost module name and then go for elaborate, okay, which is the next icon immediately after this vlog. So click on it. Obviously it throws an error because it couldn't be able to find this full adder in any of these libraries nor inside this work lib. So what you have to do, you have to bring that, compile it and put that particular module name inside this work lib. So how to perform that? Okay, select full adder and vlog. Okay, so when I do that, it comes here, and right now when I do this elaborate, no errors will come. Okay, because it finds its module name in the work lib itself. Clear? Yeah. So now that we have done with it, and now you could able to see that my snapshot is also being populated. Just by looking at this plus symbol, I could able to see that. Okay, so when I expand this particular plus symbol, you find this test bench of our sorry, the module name of our test bench, and then you select this, and the last option that we have here is the launch simulator. Okay, so click on this launch simulator icon, which is immediately next to the elaborate option. Yeah, so now that this simulator has got opened, and it opens up with two windows. One is the console window, the other one is the timing or the design browser window. Okay, so we'll be working with this design browser window. So select your module name. So when you select this module name of your test bench, it lists out what are the signals that has been used inside the test bench. Okay, so select this and press Ctrl A to select all the signals inside the objects sub window, and once you select all of these signals, there is an icon showing a waveform. Okay, so select that particular icon at the top. Okay, so right now this particular screen is having no information, so we have to run this particular simulation just by clicking on this play button. Okay, so when you click on this play button, you can able to see that there are waveforms, and I have to expand this. So there are two arrow marks, so just try to expand and you would get all the informations that you have specified. Okay, so let us put a cursor here, and you see when our inputs are all okay. Yeah. So you can actually go for verifying all of these things. I have already done it, and the output would change only during the positive edge. Okay, so ensure that you have the same similar kind of codes for you. Okay, yeah. So the code is working. If you want, you can verify. I will just pass it for some time. So I have this 1 1 1, and I have the cout that is equal to 1, but the sum seems to be 0. So what has happened? Why the output is not happening? It happens. Yeah, where exactly it happens? Yeah. Still the positive edge has not yet appeared. Okay, so the moment I get into the positive edge of my clock signal, which is this is the clock signal that I have, the moment I get into the positive edge, then it calculates all of these inputs, and then it throws me an output of 1 and 1 for both the cout as well as the sum. Clear? Yeah. So we have done with the verification. Now that we can directly go for synthesis process. Okay, now I close even this nclaunch because it is no more required. Now under the synthesis we have to perform few things, so I'll just talk about certain theory, and then later I will talk about the we will be using the tool to synthesize our code. Okay, Now, in order to do the synthesis, we have to get into the synthesis folder. Okay, so this is the folder name that I have kept. So I'll be getting into this folder, and then I have to invoke the command rc space -GUI. Okay, so this is the code that I have to execute. Okay, now in this, once I get into this, I have to perform certain tasks in it. Okay, the very first task is to provide the search path. Okay, so you need to provide the search path for two things. One for the .lib file location and for the .v or your HDL file locations. Okay, so this is the first step that we have to do, and the second one is to provide the library name. Okay, the library name as well as the name of your design, okay, or the .v or the HDL.v or whatever v that we have to provide. Okay, so first we are trying to set the search path, and the next thing is that we are actually specifying the name of the files that has to be used for the .lib and for the .v file. Clear? And the third one is to perform elaborate. Okay, so elaborate is one of the operations that we have to do, and later on we have to read the constraint. Now, as I said before, I have already written a constraint file, and that constraint file has to be there inside this synthesis folder. Okay, so ensure that you have something like add SDC, and also I want you people to go through it, and you have to perform certain tasks in this add.sdc. Okay, but I have already written a template for it. You have to go and verify certain things over here in .sdc file. Clear? Yeah. So ensure that this particular file is available inside this folder of synthesis. Okay, and once you ensure that, you can actually perform the read operation of this. And the fifth is to perform the synthesis process. Okay, so under the synthesis process, we will be performing two types of synthesis. One is to map our code to a generic set of cells. Okay, so generically we will be performing some synthesis process. I will talk about it. Like we have written something like sum equals to A XOR B XOR and C in XOR, right? So we will just see, like without providing our .lib file, how does this particular expression is getting translated into some real set of hardware. Okay? And that is what we will do it. And during the synthesis process under the generic name, it doesn't take any of our cells. Okay, so it just takes the generic cells and tries to map those expressions that we have given in terms of hardware. Okay, so the next thing is to go for mapping. Okay, so when I go for synthesis under mapping conditions, it goes and picks our standard cells. Okay, our NAND gates, NOR gates, D flops, everything would be used, and we can just see the visual of it. Okay, so once we have done the synthesis process, this is the most important step. Generic is just to show you like how exactly the expressions are getting mapped to real like generic hardware. Okay, and the sixth one is to write out the netlist file. Okay, so along with this netlist file, which would be with an extension of .v, we also have to write out the SDC file. Okay, so you might be wondering, like we have already given an SDC, and why this SDC is again written out. Okay, so we will be using this written out SDC file under the physical verification or physical design. Okay, or place and routing process. Okay, so this is the file that we are writing out of the synthesis tool. We'll be using in our place and routing stage. Okay, so after writing out both these files, then we can just close it by typing exit. Okay, so this is just a brief overview of what we are going to do in this synthesis process. Clear? Yeah. So let me get back to this, and again it would take some time to open up. So I'll just type the command. Yeah. So now what I'm supposed to do? First of all, should I need to invoke our command inside this RTL directory? No, right? So I have to change my directory to synthesis. So I'm just typing, and I've got inside, and I have to check whether I have this add. Yeah, so I have this add.sgc file over here. Okay, so forget about the remaining set of things. Okay, I should have cleaned up everything, but it's fine. Okay, so ensure that only this particular file is available. Okay, and don't worry about the other files that I have here, because it's already run log files that are there. So don't worry about these things. So just type in command, this rc space -GUI. Okay, so just click enter. Once you enter this thing, it will take some time for you to invoke this particular tool. And in order to perform all of these 7 operations that I've said, we have to have a tickle script or a tickle set of commands. Okay, so I'll just write all the commands directly in the terminal itself, but you just copy those commands. Okay, so totally almost like 8 to 10 commands would be there. So this is our GUI window. Apart from this GUI window, we will also have the terminal that we have used till now will have this RC prompt. Okay, so this is the command prompt, and we will be using this particular command prompt most extensively than compared to this GUI option. Okay, so first, as I said, what is that we have to do as a first step? There were 7 steps, right? Yeah, search the library path as well as the set the library path as well as the HDL path. Okay, so set attribute. So we can use the short form attr. Okay, or if you want, you can just write the complete sentence of attribute. Okay, and then we are going to set the attribute of this library. Yes, so this is a tickle command only. We can write it in a code that is also possible. Okay, so the directory name is lib, and where this library is located, or sorry, the directory name is lib, where I will find my .lib files, right? So now where exactly this library is located with respect to the current directory? Yeah, under digital we had some set of directories, right? Yeah. So as I showed here, right now I am under this directory. So I have to go to the parent directory and fetch this particular location. So that's the reason why I gave double dot and then fetching this location of lib. Okay. If you have given a different name, then change it accordingly. Is that clear? So since I want to access this particular file where I have kept all my .lib file, so I want to locate this particular directory. So right now I am currently inside this directory, so I have to go, when I use double dot, it goes to the parent directory that is in this directory, and inside this directory what I have is the directory named as lib. So I am fetching that location over there. Is that clear? Yeah. So now let me try to execute that. When I click enter, the path has been set, and similarly I want to set the path for our HDL. Okay, so even this HDL will have almost a similar kind of syntax, except the lib is being generated is being replaced with HDL underscore search underscore path, and then can you help me in writing down the path of it? Where exactly I have kept my .v files? Huh? Yeah, under RVC, which directory I have? RTL, right? Yeah. So I have it under the RTL directory. So I have to go to the parent directory and go to the location of RTL, and then just enclose this syntax and then click enter. So the paths are being set. So the second step is to read out those files, right? That is what I said. Read out the library name or the library as well as the HTL file. So again we have to go for set attribute and then the library, and I know the library name that is available under that, so which is stdlib.lib is the library that I wanted to fetch from that particular location of lib, okay, directory lib. So once I click on this, you can able to see that the directory has been read and it has 4 cells, okay. Now there is also some set of warnings that has been listed here. Can you read out what is the warning that is being telling for us? Yeah, the area is given as 0. So what I said when I went for generating the .lib file, we have to go for post processing the .lib file, okay, where the area would be there. Now you have to replace that area with the width into the length of your TR boundary, okay. So that information, if it is provided, then it will not throw this kind of warning, but it will just go ahead, okay. It is not a problem as far as the synthesis process is concerned, so we'll leave out those things. Now we also have to provide the file name of our HTL, so read_HTL, and then I have given full adder.v, okay, and this is the file name that I have given. So ensure that the file name, whatever the name that you have given, has to be given directly here, okay. So when I click on this, it will go and so get into the location of RTL code directory and fetch for this particular file, okay. If you want me to go a bit slower than this, I can. So this is phase is fine, right? Yeah. So click enter, and I think something, the specified file could not be found. Okay. I think I've given this name full add, I guess. Yeah, full add. Okay, it is not full adder. If you have misspelled your file name, again you will get some sort of error. Okay. Yeah. So having done this, what is the next step that I have to do? Elaborate. Okay. Let us see what happens when I go for elaborate and then click enter. Yeah, something is popping up at the background. Okay, so let us check for it. So in this elaborate operation, it has performed certain things for us. So let us zoom in and see. It has tried to replicate our structure. There are 2 XOR gates to realize our sum, and then the sum output has been outputted only through a flop. Okay, so this is nothing but our RTL coding. Okay, so there will be always a flop that is being associated with our coding conditions. Clear? So whenever there is a positive edge, the output of our this output would be launched onto the sum terminal. Okay, so and similarly they have it has tried to replicate our structure with the carry out using this structure. Okay. So now that we have done this elaboration, now what we do is that we'll go for constraint. Okay, so it is read_sdc, and then since my constraint file is available in the same directory, I just give this name of it. Okay, read_sdc space add.sdc. Okay, I guess the file name is true. Is same. Yeah. So you see, none of these things are failure, so everything is successful with whatever the information that we have given. Okay. In order to know what exactly all of these things, you have to watch the video that is already been uploaded. Okay. Yeah. So now that we have read the constraint, and now we have to perform synthesis operation. And as I said, there are 2 types of synthesis operation. So again, if you want, you can directly write the synthesis entire word, or you can just write syn and then space -2 underscore generic. Okay, so just click enter and see what is happening at the GUI. Okay, so the GUI has slightly got modified with some set of NAND NOR gates. Okay, but none of these gates are actually our structures. Okay, so it has tried to build with XOR gates and stuff like that. Okay. So there is a slight difference between this elaborate operation and this generic operation. So it would be a kind of question for you during your viva. Okay, so what is the difference between the elaborate and the generic operation? Okay, so this is not fascinating me, but what fascinates me is basically the next step. Okay, so the next step is almost the same identical syntax. The only thing is that to generic has to be changed to map. Okay, now when I click on enter, you just see what are the cells that we have designed. Okay, inv1 x1, so and nor 2 x1, and even the flop is dflop dff bx1. So these are the blocks of ours which has been used to build our logical expressions that I have listed. Okay, so the sum is basically was previously built by making use of the XOR gate, but right now we don't have any XOR gate in our library, and due to which the tool has used an equivalent circuit by making use of all the universal gates in our standard cells, and it has replicated this entire 2 XOR gates with this structure. Okay, so when I got for the first time, I was like too much fascinated about it. Okay, yeah. So now that we have generated the netlist, we have to write it out as a netlist. Okay, so now we are getting into the sixth step, where there is also one more thing. We also can see the timing reports. Okay, so report underscore timing would help us to know if there is any slag or not. Okay, in our design for the given clock period. Okay, so I have given a very large clock period of 40 nanoseconds. Okay, which is way larger than to really compute these things and then throw an output. Okay, so it just takes a fraction of nanoseconds to complete this entire process. Okay, so let us see what happens when I give this report timing, and you would find that there is a huge time slag. I think the arrival time is here. Timing slag is unconstrained. Okay, I will just check for this. You actually have to have some numbers here. I think I have to fine tune my SCC file. Okay, later I will talk about it. Okay, so you will have some sort of numbers which is positive. Okay, which is more than 3000 change I was getting it. Okay, so I think I have to change my SGC file a little bit. Okay, I'll come back to this later, but you will have a large number over here. Okay, now your task would be to fine tune this number to somewhere around 100. Okay, so you have to fine tune your clock period, reduce the clock period or increase the frequency of it, such that you end up having a time slag which is just around 100 nanoseconds. Clear? Yeah. So that is your task, but that is not my work. So I'll just go for the next step, which is write out our files. Okay, write HDL, and then you have to put a write arrow. Okay, and then just give full add underscore netlist .v. Okay, so through this command, what we are actually doing is that we are trying to generate a netlist out of the synthesis process. Okay, so and then as I said before, we also have to generate the write out our SDC file. So write underscore SDC space, and then the right arrow key space, and then full adder, and I'll just change this name with a different extension, full add dot SDC. Okay. So make sure that this SDC file name is different from what we have already used. Okay, so otherwise it will override the previous SDC file. So I'm just giving a different name, and it does complete the SDC export operation. So now the last command is to exit this particular tool. Just type exit and click enter. Okay. Now what I do is that I'll just try to open up this this generated netlist. .v, okay, and see what is there inside this. Okay. Now you get able to see that. Can you just guess like what type of coding that you can expect inside this netlist file? There is something known as behavioral, what else do we have? Data flow, yeah. So what type of, among those three, data flow, yeah, so you know the answer, right? Yeah, that's good. Yeah, so that is what we can expect here, okay? So you see all our modules are being called, and then it has given some sort of name for it, like the instance name, and then it puts all our input and connects our outputs, and then everything is being done, okay? Now, when I go for simulating this particular full adder, okay, when I go for elaborate operation, will our code, the generated netlist, will throw an error or not? Will it throw an error or will it not throw an error? If I go ahead with this full adder underscore netlist.v file, when I run this particular file under nclaunch, will it throw an error? Yeah. Why? Yeah, these module names are missing. Under the work lib it is not there, nor under any of the libraries it is not there. From where I can get those module names or the functionality which is inside this deflop or NOR gate or inverter? Yes, because this is the topmost module according to my design. This is the topmost module. Okay? The next topmost module would be my test bench. But under this design topmost module, it needs these many modules to be attached to it. Okay, so obviously during the elaboration it will fail. But how will I encounter this particular issue? No, where does this module names would be available? Huh? Yeah, yeah. Which one we have created? Lib or lib? Yeah, under the lib directory or using this liberate tool, what we have done is that we also have generated two Verilog files. When you open that Verilog file, it will contain the module definitions of this deflop, NAN, NOR, everything would be there. Okay, so that's the reason why we not only generated .lib file, we also generated two other .v files. Okay, let us see and open and check what is available inside that. Okay, so before that I just copy this full adder underscore netlist.v file. Okay, so I just copy and then full adder underscore netlist. I go to the parent directory and then I have to get into this RTL directory and then click enter. So this file would be copied into our RTL directory. Clear? So I've just copied it and I just get into this directory of RTL and see. Yeah. You see our so our full adder underscore netlist.v file is already been located right now. Okay, but as I said before, all of our .v files has to be there inside this particular directory. So we also need those two files that we have generated under the .lib, under the lib directory to be present here. So what I do is that I just again go for copy command. If you know the file names, you can actually directly access it. So I'm going to the parent directory and then I'm getting to the directory named as lib, and inside this lib I have, I think small letter I guess, d.v. So that is the file that I am copying into the current directory. So click enter, and similarly the nd.v file also I am copying it. Okay, so now that when you press ls, you will find all of the files that is required for this particular simulation purpose. Okay, so this file and this file, those are the two files that I have. Now before I invoke the tool and then try to do the simulation, I just want to see what is there inside this and how does our modules are being. Okay, so I'll just go with nd first, nd.v. So in the case of non-delay, okay, where there is no delay between the input and output, this is the definitions that we have. Okay, so you have this deflop and it defines the input and output ports, everything, and then there are a lot of other information that it contains in it. Okay, so we will not worry about these things. But what we do is that we will try to open up the other file that we have, which is d.v. And when I look here, there is slight difference between this definition that I have under this d.v and this nd.v. Okay, so you can able to see that this timing is being elaborated with different factors here. Okay, so again you could able to see that spec param, and there are certain numbers running between the colons. Correct. Now, what does this first set of value denotes, and what is the second set of value denotes, and what is the third set of value denotes here? Not exactly. No. When we used our we have used this spec param when we were working in .lib file generation. No, there is something known as average. There is a table format that I gave, table style, and then space, minimum, colon, average, colon, and then maximum. So that is the syntax that we had given. So whatever we have here is all this minimum delay, and the average delay, and the maximum delay that it can have. Okay, so it applies all the different type of input slew as well as the output loads, and tries to compute what is the maximum value that I've got, what is the average value that I've got, and what is the minimum value that I've got. Okay, and those calculated values have been based on to this. Okay, so for more information regarding your queries, you have to watch the videos. Okay, yeah. So that is the difference. So I will not spend much time here. So what we do is that we'll just directly invoke our tool nclaunch. So now, obviously we have to, if you want, you can clean up this particular workload. Okay, so because we already have this modules that has been listed, but we don't require any of these modules right now. It is not really required, but if you want, you can do this. Okay, so right click and click on delete content, not on delete references. Okay, so click on delete content, it clears all the contents that are there in the workload. So now when I go here and then click on this full add underscore netlist.v, I have that topmost module name. Okay, and then I have to select my test bench. Okay, so when I click on this, even that module name is also there. Okay, so I have this top module. Can I go ahead and do the elaboration? No. Still, what else we have to do? Yeah, I have to have all the module definitions of NAND, NOR, deflops, everything, right? So those are available in both these files. Okay, first what I do is that I'll just go ahead with non-delay. Okay, where there is no delay between the input and output. The moment I apply my input, the output would appear. Okay, so with that, we'll try to first check it out. Okay, so just select this and go for vlog. When I do this, obviously the list would be filled with so many of these things. Okay, so don't ask me what are the other things that I have. Even I don't know. So among this, which is my topmost module that I have here among the list that I have? Deflop, DFF, DX1. That is the topmost module. Full adder is the topmost module, or test bench. Test bench, right? Yeah. So select the test bench, and then we have to go for elaborate. Okay. So test underscore FA is the module name that I have given. So I select that and go for elaborate. Something is there. Yeah. So something has been popping up. So what does it say is that there is something known as time scale directive that is missing. Okay. What I do is that I'll just close this because I don't need to close this. So when I open this netlist that I have generated out of the synthesis process, okay. When I open this, the module name starts without any time scale parameter, and that is the reason why it is throwing us an error. Is that clear? So what we have to do is that we have to define the time scale. I think for you, just open it in gedit so that it will be easy for you to see. Okay, so I'll open the other file that I had already designed. So that also has this time scale unit. So copy this time scale and then paste it on top of this and save this, and then when I go back here and try to run the same test underscore, once you're done with it, you have to recompile it because the netlist has been newly done, so we have to recompile And once you recompile, go for elaborating your topmost module, which is test_fa. So now there is no error, and we can just expand the snapshot and select this and go for simulating our design. So again, it will take some time. Okay, what we can do in the meanwhile is that we will compile this ND as well. Okay, so that so when I compile this, what happens is that whatever the names that I had already here would then be overwritten by the module name that I have defined inside this inside this d.v. Okay, because the module names in both the files will be the same. Okay, the only difference is the timing parameters. Yeah, then your tool has been opened, so we'll go one after the other. Okay, so teach me how to do the simulation part. Okay, so select the design browser. First close this. Yeah, and then okay, yeah. Control A. Yeah, and then choose this waveform and click on it. Yeah, I've done it. And which play button? This one? Yeah, this one, right? Yeah. So select this and run it, and try to expand this, and just see. We'll just take a random point. Okay. So see whether the corresponding inputs is providing us the proper output. So I have b equals to 1. Obviously, the sum is supposed to be equal to 1, so we are having it. We'll also check one more set of things. I have both a and b that is equal to 1, 1, and carry out is 1, and the sum is equal to 0. Okay, so we could able to reproduce the result. Okay, so now note that I just want to zoom in and see that the moment I provide an input, the outputs are produced immediately. There is no time delay between the input and output. Okay, so what we do is that we'll try to recompile the other one. Okay, so see what happens and what is the difference between this d and nd.v file. Okay, so I'll just recompile this guy, and it has been compiled, and the only thing that I have to do is that go for this, elaborate only the test_fa, and then again go for this and since you are already familiar with these steps, so I'm just quickly doing it. And let us move to a particular point where I have some sort of delays. Okay, so you see there is an input. What is this input? Yeah, the clock. And the carry out is generated after a while. Okay, so it is not immediately the moment it finds the clock positive edge, it is providing an output. So there is a certain delay, and the delay is much higher for the carry out than compared to the sum. Okay, so that is the kind of output that you can observe with this d.v file. Is there any doubt in this? The difference between nd.v and d.v? Because there are a lot of gates involved. When I showed that simple schematic, right, you would find that along that particular path there were a lot of gates. So each gate would add up to a certain delay. So whatever we have done till now is all not to the depth of it. It is almost like to the topmost part of it. Like right now, you can ask like what type of data that I have chosen, whether I have selected the minimum delay or average delay, which delay. I've just run without any specific instruction. Okay, so under this condition, I guess it would take only the average delay and compute. But you can actually go for different process coordinates and tell the tool to pick a particular delay, and then see whether can you able to meet all the timing constraints for that all the conditions or the test corners that we have. Okay, so those are the additional work that you can do it. But for lab point of view, those are not there. If you could able to do this point,